Okay. So, the next thing we are going to look at is what kind of clusters are being produced by the Lloyd's algorithm, right. So, we know that the algorithm converges, but what can we comment on the type of clusters that results from this algorithm. So, to take a simple case, let us look at the case first when k equals 2. When you have a bunch of data points, you just want to divide them into 2 buckets or 2 clusters, right. So, let us say Lloyd's algorithm is run with just k equals 2 and Lloyd's algorithm produces 2 clusters. It will converge and it will produce 2 clusters with means, let us say mu1 and mu2. Let us say the algorithm converges and then we in the converged partition clusters we look at the average of cluster 1 and average of cluster 2 and it turns out to be mu1 and mu2. Now, the question is what can we say about the points assigned to these clusters? Assigned to cluster 1 and cluster 2. Let us say cluster 1, let us say we focus on cluster 1 now, the argument for cluster 2 will be similar. Can we say something about how do the points look like? Well, by algorithm construction and the convergence argument that we did earlier, we know that when the algorithm said, hey, the partitions have converged, it means that every data point is happy with their own mean. What does that mean? Well, if you look at cluster 1, then it means that each data point that has been assigned to cluster 1 is closer to mu1 than mu2 in terms of distance squared. That is what it means, right. So, it means that for cluster 1, for points in cluster 1, x minus mu1 squared is less than or equal to x minus mu2 squared, where x is of course a generic point in cluster 1, right. So, its distance squared to mu1 should be at most the distance squared to mu2. Now, what does this mean I mean, how do we understand this? So, we can think of this as mu1, this as mu2. Let us say I just give you mu1 and mu2 and I ask where could be these clusters. Now, we know that points assigned to cluster 1 satisfy this equation, but what is this equation? Let us unravel this equation a little bit and see what happens. So, this is just x squared plus mu1 squared minus 2 x transpose mu1, and that is less than or equal to x squared plus mu2 squared minus 2 x transpose mu2. Of course, we can cancel certain terms and what would result is the following. I can bring the last term to the other side. So, that would mean x transpose mu2 minus mu1 is less than or equal to mu2 squared minus mu1 squared by 2. What is this? So, this is for all x in cluster 1, it must be the case that this is satisfied, simply because the distance of the points to mu1 is less than mu2. Now, what does this mean, right? So, pictorially, where are these points, right? So, that's something that we want to understand, right? So, if this is mu1 and mu2, how can we say where are the set of points which satisfy this equation? This, as you can already observe, this is an equation of the form, x transpose some w is less than or equal to some b, right. So, it is linear in x, that's what we observe. So, which means we should expect some kind of linear division, and let's see what that is, right. So, here is a picture. We have mu1, let us say this is mu2 and we want the equation is mu2, my x transpose mu2 minus mu1 is less than or equal to mu2 squared minus mu1 squared by 2. Well, basically the dot product of your cluster point x with respect to mu2 minus mu1 is at most something. That's what this is saying. But let's look at where is the vector mu2 minus mu1. Well, here is the vector mu2, right? So this is mu2, this is mu1. Where is in this case? Let me just confirm the order. I got the order right here. Sorry, but there, yeah, this is correct. Okay, so where would be mu2 minus mu1, right? So mu2 minus mu1 is what you would add to mu1 to get to mu2, which means it's this, right? So this is what you would add to mu1 to get to mu2. That is your mu2 minus mu1. So which means the actual vector is from the origin pointing in this direction, right? So that is my mu2 minus mu1 vector. This is where the that vector is. Now we know where are the set of points which make a 0 dot product with this vector. Well, that would be somewhere here. So this would be set of all x such that x transpose mu2 minus mu1 is 0. But our condition says that x transpose mu2 minus mu1 is at most mu2 squared minus mu1 squared by 2, right. So now whether that value is positive or negative will depend on which length is bigger, mu2 squared's length is bigger or mu1 squared's length is bigger. At least in this picture it looks like mu2 squared's length is larger than mu1 squared's length. So this seems to be a positive quantity. So which means if I want if I ask the question where is x transpose mu2 minus mu1 is less than or equal to, instead of less than or equal to, if I put a equal to and ask where is it equal to mu2 squared minus mu1 squared by 2. In other words, if I ask where are the set of all x which satisfy x transpose mu2 minus mu1 is equal to mu2 squared minus mu1 squared by 2, well, because we are thinking of this as a positive quantity, that means that I have to move the green line parallel in this direction, right. So, so that would give me a line, let's say like somewhere like this. Now, this could be the line which is x transpose mu2 minus mu1 equals norm mu2 squared minus norm mu1 squared by 2, right. So then where is our cluster 1? It says that any x that is in cluster 1 should satisfy something, it has to be less than or equal to this, which means that it has to be in this region, right. So left of the orange line, this is the region for cluster 1 region. Now, this is one way to think of this directly from the picture. Now, we can also ask, well, how much did I move on to the right, right? So, I did move the green line parallelly to the right. So, how much did I move? Well, can we find a point which satisfies this equation? Then we will know, right? So, one point that satisfies this equation is like take x equals mu1 plus mu2 by 2, which is the average x, right. So, average of the means. So, now then mu1 plus mu2 by 2 transpose mu2 minus mu1, you can verify, will equal mu2 squared minus mu1 squared by 2, which means that the average of the means is actually here, right. So, the average of the means is exactly this point. This point is essentially then saying this is mu1 plus mu2 by 2. So, this is just mu2 squared minus mu1 squared by 2, which means this point, which is the average of which is between mu1 and mu2, actually falls on this line, right. So, which is in fact this is mu1 plus mu2 by 2, right. So another way to think about this is to simply say that, well, I have 2 points, and then I want to understand the set of all points which are closer to one point than the other. Well, I connect the line between these 2 points, look at the perpendicular bisector of this line, and then say that every point that falls on one side of the perpendicular bisector are closer to that point than the other, which is exactly what we have kind of argued in a general sense in high dimension as well. Okay, so this is good. So this just means what happens in 2 dimension, when k equals 2. Let me just make sure that, well, if this is cluster 1, well, where are cluster 2 data points? Cluster 2 are on this side. So basically what has happened is that so your K-means algorithm or the Lloyd's algorithm is going to give you clusters if k equals 2, which are separated by a line. That's what this means, right? So it has to happen. This simply comes from the convergence criteria for our algorithm, right? So that implies this. Okay. So now what happens when k equals 3? That's a natural question we can ask. And we'll see that, and that might give us some more intuition as to how these clusters look like. Okay, in k equals 3, the algorithm is going to converge with not just one mean, but then 3 means. Not just 2 means, but then 3 means. Let's call these means mu1, mu2, and mu3. Let's say, again, the data is just 2-dimensional data. I mean, all of whatever we are saying works for high-dimensional data also, but then it's easy to visualize the 2-dimensional data. That's why we are doing this. Okay, so now what is the question we are asking? Where are the points which are assigned to cluster 1? That's the first thing that we would like to understand. Now, we know that by the convergence criteria of Lloyd's, every point that is assigned to cluster 1 is closer to mu1 than mu2 or mu3, right? So, both of them, I mean, if I compare, even if I find one of the others, mu2 or mu3, as being closer, then I would have jumped, the algorithm would not have converged. So that cannot be, these mu's cannot be the final mu's. Because the algorithm is converged, every point assigned to cluster 1 necessarily should have distances to mu1 closer than both mu2 and mu3. So how does that look in picture? Well, first, where are the set of points which are closer to mu1 than mu2? Well, we already argued that that is going to be simply so let's say if I put this imaginary line that joins mu1 and mu2, then that is just going to be in the, the left hand side of the perpendicular bisector of mu1 and mu2. Now, okay, mu3 need not be on this line. Mu3 could be somewhere here also, right? So this line is like this. But we are also saying, just for consistency, I'm going to use the green color here. Right, so anybody on the left hand side of the green line is closer to mu1 than mu2, but that is not enough to say that a point can be assigned to cluster 1, right? So it is also necessary that the point should be closer to mu1 than mu3 also, which means that I need to also look at the perpendicular bisector of the line joining mu1 and mu3, and that may be somewhere like this, and it can go further. Why that further is not that necessary, but now it means that, well, the points assigned to mu1 are on the left hand side, or the direction that I'm drawing here, with respect to mu3, and should also be on the left hand side, that is the direction I'm drawing here with respect to mu1, which means if I had to shade that region where the points are in cluster 1, it will be an intersection of these two regions, which will exactly be this, right? So it will be, the boundary would be something like this. Now, what about mu2 and mu3, right? So where are the points in cluster 2 and cluster 3? Well, for that we need to draw one more perpendicular bisector which connects mu2 and mu3, and that would be somewhere like this. And that would tell us those assigned to cluster 2 are going to be in this region. Right, so this would be my boundary. It's closer to both I mean, it's closer to mu2 than both mu1 and mu3, so it should be in the blue region. Naturally, whatever remains is the ones that are for the mu3 region, which is in this region, right? So as you can see, what has happened is that you have three different separators, one for each pair of means: mu1, mu2 separator, mu1, mu3 separator, and mu2, mu3 separator, and then the points assigned to mu1 are closer to mu1 than mu2 via the mu1, mu2 separator, and mu1 than mu3 via the mu1, mu3 separator. So essentially what we are doing is that we are dividing the entire space, in this case R2, which is where the data points are, into k different regions using intersection of half spaces. Basically, when I say half space, it means that in 2 dimension you draw a line, and anything on one side of the line is what is called as a half space. It's dividing the entire space into two parts. A half is on one side of the line, the other half is on the other side of the line. So there are, for every data point, so for every cluster, now your region would be an intersection of k minus 1 half spaces if you have k clusters to begin with, because every point is going to get compared with, every mean is going to get compared with k minus 1 other means, and then it should attract point towards itself. So it will be an intersection of half spaces. So cluster regions are intersection of half spaces. So this argument works even for high dimension. We are visualizing in 2D, but then it's true for high dimension as well. And these type of intersection of half spaces, they also have a name. This is called as Voronoi region. Voronoi regions. Right. So basically, what that then tells us is that if you run the Lloyd's algorithm, then the clusters can be imagined as if they are falling in different Voronoi regions. Basically, your Lloyd's algorithm is trying to find the best, in some sense, Voronoi partition that will lead to, in some sense, the best cluster, right? So you necessarily, the partition, the points assigned to each cluster should be part of a Voronoi region. That's what this argument finally says, right? So this is the comment that I wanted to make about the nature of clusters. Let me also at this point make a comment about something that we perhaps won't discuss in this course, but then it's interesting to know also. So for example, if I had data in 2 dimension like this, right? So let's say I had data around a circle like this, and I had some more data points in a smaller circle like this, right? Now, the number of clusters in this data set naturally looks like 2 clusters, and 1 cluster which are in the outer concentric circle, and the other cluster are the points in the inner concentric circle. Now, let's say I give you this data set and I ask you to run the Lloyd's algorithm with k equals 2. Of course, it's going to converge, we know that, but what kind of partitions would it result in? In other words, where would these points get clustered to? How would these clusters look like? Now, if you think about that, we know from the previous argument that the clusters necessarily have to be in Voronoi regions. If k equals 2, then it means that there is a line that divides cluster 1 from cluster 2. Now, if the points are in the circles, maybe you might get a line something like this. It's not necessary that it has to be a slant line. It could be a vertical line. I mean, that the exact line depends upon the exact spacing of these points and so on. But irrespective of how the points are spaced, it's going to be a line, which means that I'm going to say anybody on this side is in cluster 1 and all the points are on the other side are in cluster 2. Which means we did not recover the real clustering that we want, which was the inner concentric circles should become 1 cluster, the outer concentric circle should become another cluster. your K-means algorithm in the way that we have described it will never be able to recover such a partition, because the nature of clusters are Voronoi partitions. So if your data set, if you don't believe that if your data set has a nice Voronoi like structure where the partitions, where the clusters sit, then perhaps your K-means algorithm is going to fail there, right? So it won't be able to recover. Now, how to fix this, right? So how to fix? So we won't do this in detail in this course, but let me at least give you some pointers which you can perhaps, if you're interested, you can go ahead and read about these things. So like how we argued in PCA that if your features are non-linearly related, then you can use this notion of kernels to go from low dimension to high dimension, and in the high dimension you learn a linear relations, which translates to nonlinear relationships in the lower dimension. Similarly, there is a way to, kernelize K-means. It's called the Kernel K-Means algorithm, and it has interesting relationships to other types of popular clustering algorithms also, which we are not seeing in this course. For example, something called as a spectral cluster, which has a lot of relation to PCA as well, right? So in simple terms, you can understand this as if, maybe there are no Voronoi regions in the low dimensional space that gives me natural clustering of this data, but then if I map it to some high dimensional space, then it would kind of, the natural clusters would kind of separate out into different Voronoi regions, and in the high dimensional space I can do a simple Lloyd's algorithm. That's the basic idea. So to go to this high dimensional space without really, the problem of computational efficiency and so on, inefficiency and so on, we use the kernel trick, and you can kernelize K-means also. Let me leave it at that, without dwelling into depth about how to do this kernelization. But it's good to know that you can kernelize K-means also, and this kernel version of K-means has a lot of relation to, computing the eigenvectors of your kernel matrix and then using them somehow as some representation of these data points to do further clustering. We won't really look at that in this course, but it's good to know. Okay, so that's all I'm going to comment about the nature of clusters that Lloyd's algorithm produces. We have two more issues that we need to talk about. One is the initialization issue. How do you initialize Lloyd's algorithm well? And the second is the issue of how do you choose the number of clusters K. First, we will talk about the initialization issue now.